have to give Ampere's law the differential treatment. Ampere's law is the one where we have H dot dl is I enclosed. Okay, and the way we get I is it's the surface integral of the current density. Current density is in amps per square meter, usually. Okay, current density. Describes how much current is flowing through a particular point. A nice red marker on there, easier to see. So, as usual, I'm going to do this really quick. We've done it before. We're going to turn this into a surface integral, equate them at each point, and we're getting curl of H equals J using Stokes' theorem. We've got Ampere's law in integral form right here, differential form right here. Differential form. Oh, I wrote that real small. Differential form. Okay. So then a curious person comes along and says, let's take a time derivative of these things, see what happens. Let's apply an operator to it. Let's see what happens. Let's just be somebody who does a lot of math and see what happens. And then that's how we get in trouble. So we're going to apply divergence operator to both sides. Okay. And just using math, and you can work out the components of this just in a matrix. I'm going to do a dot product of this divergence operator with the curl, and it's going to be 0 because math. Right, now this one over here, not necessarily 0. Okay, the divergence of the current density is talking about how much current is flowing out of a surface. Okay. We can hook that back in and go, it's related to the if we took this and we put it inside a volume integral, we're going to get J dot ds back using the divergence theorem, and this is describing a current. It's describing, and this is a closed surface, for example. This is describing how much current is flowing out of a little volume surrounded by this surface. Flowing out of a volume. It's the rate of change of charge contained inside that volume. Okay, by the continuity theorem. If stuff was leaving, then that much stuff must have left. It sounds a little bit repetitive. It's the rate of change of the enclosed charge. Okay, or if we think of it as happening at a point, it's rate of change of charge density. And if it's positive here, that means there's charge leaving, so we have to put a minus sign on it. And so when you take that continuity idea and you work it back to what's happening at a point, this is a negative rate of change of charge density. Not necessarily 0 every time. So just like before when we were missing a piece, okay, this is magnetostatics. We have constant currents, those aren't changing with time, and we got this result for Ampere's law. There's another piece that has to add on to make this come out 0. And that piece, we know it has to be this to cancel out. And we can take it another step further because we know something about charge density from Gauss's law. To make the math. Okay, write that over here. Gauss's law in differential form is divergence of D. Is going to be, looks like P. Divergence of D is charge density. Okay, so we can work that in. D dt divergence of D. Okay, so we can put all that stuff back together. If we're going to take the divergence of something or the time derivative, it doesn't really matter what order. We can go divergence of d dt. And no wonder this didn't show up before. This little extra piece didn't show up before because we always had static electric fields. And their time derivative is worth 0. Okay, so putting it all together, this corner down here, Ampere's law is the curl rate equals J plus dd dt. Differential form. And you can still sort of use the idea that there's a current in here, J is current density, to map it onto Ampere's law, current amps. Not a coincidence.